Hello, I'm Ed Llewellin and I'm Professor of Volcanology at Durham University. I'm delighted to have been invited to give this talk as the recipient of the 2021 VMSG Annual Award. I've elected to focus my talk on the rheology of magma and lava, which is a topic that I've worked on and off throughout my career. I will focus on the current state of the art and give a personal view of the future of the discipline. Why do we care about rheology? Well, whenever magma experiences stress, rheology dictates how it moves in response. In this example from the 2018 Lower East Rift Zone eruption of Kilauea, low viscosity magma moves easily when a stress is applied, leading to gentle fountains and flows. And rheology dictates how the vents localize and where the flows will go. Here, magma is 100 million times more viscous than we just saw, but it can still ooze slowly, as shown here in the 2006 eruption of Mount St. Helens. And the rheology dictates the morphology of the dome. But high viscosity magma also has a tendency to erupt explosively, as in this eruption of Colima in 2017, and rheology dictates whether and when magma will fragment to form an explosive eruption. So rheology is important throughout magma's journey through the crust and over the Earth's surface, and there are many questions that require an understanding of rheology, and they include some of the grand challenges in volcanology. One of the reasons that these questions are hard is because magma is such a rheologically complex material. Viscosity, which is the most important manifestation of rheology, varies over more than 10 orders of magnitude for pure silicate melts, depending on chemical composition and temperature. But magma is rarely a single-phase melt. It is invariably a multi-phase suspension of liquid melt, solid crystals, and gas bubbles, and the componentry has an enormous impact on viscosity and also introduces all manner of non-Newtonian behaviours. The rheology of multiphase suspensions also depends on the nature of the deformation experienced by the material, and for non-Newtonian materials, the apparent viscosity depends on the strain rate, that is, how fast the material is being deformed. Perhaps the most complicating factor is that composition, temperature, componentry, and deformation can all vary dramatically in time and space as magma moves through and over the crust. We can illustrate this evolution by considering how magma moves through the componentry ternary diagram as it moves through the volcanic system. So here we have an idealized cartoon of a hybrid effusive explosive eruption, and this could be a silicic eruption like Chaiten in 2008 or a Hawaiian fountain that produces rheomorphic lava flows. So at depth, we start with something close to a pure melt. So that plots over here in the bottom right-hand corner of the ternary diagram. As that melt rises, it likely stalls in a crustal reservoir where it undergoes some degree of crystallization, moving towards the bottom left corner of the ternary diagram. And it may even become a locked mush. We then have some triggering event, perhaps bubble formation in that mush, that causes separation of a melt with a low crystal and gas content, leading to a discontinuity in the componentry of the magma during ascent, which is illustrated by this dashed line on the ternary plot. As that magma then ascends, decompression and exsolution drive dramatic bubble growth, moving the magma towards the pure gas end member on the ternary diagram. And if that growth is sufficiently rapid, then the magma can fragment, which leads to another discontinuity following gas escape. These fragments may then re-weld either in the conduit or outside the vent, and then there is a further growth of bubbles as the volatiles continue to exsolve. And then finally, there'll be loss of bubbles and perhaps growth of crystals during transport, which leads us to this variably crystalline and porous final rock. So during its journey, the magma has covered almost the whole of this ternary diagram and will have been experiencing simultaneously changes in the major element and the volatile composition in the melt, changes in temperature of the melt, changes in crystal and bubble size and shape, and also changes in the shear environment. But despite this daunting complexity, we've made great progress over the last few decades in understanding the rheology of multiphase magma. And I'll use this illustrative journey to give a brief, and I should say very incomplete, overview of the current state of the art, and I'll highlight some frontier topics where progress is needed. The rheology of pure silicate melts is fairly well understood. Direct measurements of the viscosity of supraliquidus melts and metastable melts just above the glass transition temperature have been made over a very wide range of major element compositions, volatile contents, and temperatures. And these data have been aggregated and analysed to produce general models for melt viscosity. The most widely used is probably that of Giordano et al., published in 2008. And for this, you just plug in the major element composition, the water concentration, and it gives you the viscosity as a function of temperature. But there is still a lot more work to do. These general models are only as good as the data on which they are built, and further data would be very valuable for some compositions, perhaps most notably for peralkaline compositions. Even more valuable would be a deeper theoretical understanding of the molecular controls on viscosity. A complete theoretical model would allow viscosity to be computed ab initio from composition. And there's some very promising work by Llewellin and Giordano and others that has used Raman spectroscopy to investigate melt structure and relate that to the viscosity. This is an important step in the direction of a general theoretical model. There is still more work to do to understand the relationship between viscosity and melt failure. There was seminal work by Dingwall and others in the 90s that demonstrated the importance of strain rate and structural relaxation time in determining the failure of pure silicate melts, the product of strain rate and structural relaxation time being the Weisenberg number. More recent work, such as that by Wadsworth et al., shown here, has shown that failure is not binary, and there is a transitional region in which small fractures form and heal depending on stress and thermal conditions. So this plot shows the number of cracking events as the melt is deformed at different strain rates, and these are identified as acoustic emissions. At low strain rates, indicated by low Weisenberg number, we see that cracking is rare. At high strain rates, again, cracking is rare because usually only a small number of cracking events are required for the material to fail completely. But at intermediate strain rates, at intermediate Weisenberg numbers, a large number of very small cracking events leads to plastic behavior of the melt. So continuing our journey now, what happens to the magma rheology as the magma begins to crystallize? Well, this is an area that I've worked in with collaborators, notably Sebastian Müller and Heidi Maeder, and we used analog materials to investigate the rheology. And analog materials have some advantages over working with natural magmas. For example, it's easier to control the experimental and material parameters. It's also obviously safer and easier to work with. And it's also simpler because disequilibrium can be avoided so that the systems are stable and don't change their textures over time. And the major disadvantage, on the other hand, is that the complexities of the natural system are not captured. So we'll first focus on experiments with spherical particles. These show that the viscosity, as particle volume fraction increases, the viscosity increases slowly at first and then very rapidly as the crystal content goes up. The viscosity increases as crystal fraction increases because the fluid has to do additional work due to the presence of the particles that deform the flow lines in the fluid. And we find that the viscosity tends towards infinity when the maximum packing fraction is reached. And this is the point at which the particles lock up and we get a jammed suspension. This behavior can be captured by a simple relationship between the viscosity, the particle fraction, and the maximum packing fraction. Experiments with non-spherical particles have shown that the maximum packing fraction depends on the shape of the crystals. Viscosity increases more rapidly for particles of higher aspect ratio. This effect is well captured by taking into account the changing maximum packing fraction with aspect ratio. So we can see that the maximum packing fraction is a maximum for particles with an aspect ratio near 1 and becomes much lower as the particle aspect ratio deviates further from equant. So the major disadvantage of analog experiments is that they don't capture disequilibrium processes. Disequilibrium leads to crystal growth during deformation, which can have an important influence on rheology. We're just starting to understand this thanks to work by Stefan Kolzenberg and others. So in these experiments from Kolzenberg et al., the crystal growth is tracked during rheometry, which helps us to understand better the influence that changing crystal fraction has on rheology. Our understanding of rheology of crystal suspensions is best at low concentrations and becomes much shakier as we approach the maximum packing fraction. Indeed, magmatic systems can crystallize to well above the maximum packing fraction and still accommodate strain. So more work is required to constrain the rheology of concentrated and superconcentrated suspensions. This is particularly important for understanding the relationship between rheology and the mobilization of crystal mushes. There are fundamental aspects of the rheology of particle suspensions that are still not understood. For example, we don't know what the controlling timescale is for particle suspensions. For pure melts, the controlling timescale is the structural relaxation time. For bubble suspensions, we have the capillary relaxation time, as we'll see in a moment. But for particle suspensions, it isn't clear what the timescale is. And this means that we can't normalize strain rates to arrive at a non-dimensional description of shear thinning behavior. And as a consequence, at the moment, we have a rather unsatisfactory situation where we use the Herschel-Bulkley formulation to relate stress and strain rate. But this behaves very poorly at very low and very high strain rates for shear thinning and shear thickening materials. And so an important future goal is to find a better alternative. If we follow our mobilized magma as it ascends through the subvolcanic plumbing system, decompression and degassing cause bubble growth, so that we have to start to care about the effect that bubbles have on rheology. Here, experiments with analog, synthetic and natural magmas have led us to a fairly mature understanding of rheology of bubble suspensions at modest gas volume fractions. We find that the effect of bubbles is strongly dependent on the shear environment, and whereas crystals always increase the apparent viscosity of the magma, bubbles increase the viscosity at low strain rate, but decrease the viscosity at high strain rates. The viscosity of bubble suspensions can be expressed as a function of the gas volume fraction and the dimensionless capillary number, which is the product of strain rate and the bubble relaxation time. This shear thinning behavior has important consequences for the velocity profile within flowing bodies of bubbly magma, tending to form lubricating low viscosity zones where strain rates are high, typically at the flow margins. There is still a lot that we don't understand about bubble suspension rheology. A significant issue is that rheometry of natural bubbly magmas and analogues do not always agree. So here we have some experiments from Voner et al. And in this plot we have a model prediction based upon analog experiments, and these are the data from the experiments on natural bubbly magmas, and we can see that they don't match. The solution here is perhaps to conduct paired investigations where analogues are designed to match the textural characteristics of a specific natural sample as closely as possible, and then rheometry is done on both the natural and the analogue material. This will help us to understand what important complexities are missing from the analogue work. As with particle suspensions, bubble suspension rheology is best understood for low and intermediate suspended fraction. More experiments are required to span the gap between bubble suspensions and foams. In natural magmas, bubbles ubiquitously coalesce, break up and outgas during transport, and we do not have a good understanding of the impact of these processes on rheology. And while shear viscosity is fairly well understood, viscoelasticity and bulk rheology, which determines the response to volume change, require further investigation. The rheology of two-phase suspensions, so suspensions of crystals or suspensions of bubbles, is moderately well understood though. As we have seen, many gaps remain in our understanding. But understanding of the rheology of three-phase suspensions is by comparison in its infancy. Analog experiments have revealed interesting and sometimes superficially counterintuitive behavior. So here we have a plot of the viscosity of a three-phase suspension against the particle volume fraction that is then contoured for the bubble volume fraction. As you can see, at low particle fraction, bubbles increase the viscosity, whereas at high particle fraction, bubbles decrease the viscosity. But this is not a capillary effect. It's different from the effect that we saw earlier on. All of these experiments are in the low capillary number regime where bubbles should increase viscosity. However, bubbles also act to push the particles apart, which decreases their impact on the viscosity, and at high enough particle fraction, this effect dominates. These experiments have allowed us to validate a simple model for low to intermediate total suspended fraction. The rheology of three-phase suspensions is simply the convolution of the effect of bubbles and the effect of crystals. In this scheme, we treat either the bubbly liquid as an effective medium that is suspending the crystals, or we treat the crystal-bearing liquid as an effective medium that is suspending the bubbles. And which approach we adopt depends on whether the crystals are much larger than the bubbles, or whether the bubbles are much larger than the crystals. But this doesn't work if the crystals and bubbles are similar sizes, and more generally, we don't have a good theoretical understanding of how to determine rheology when the interactions among the various suspended phases are important. And this is not just the interactions between bubbles and crystals, but also between populations of crystals of different sizes and shapes, and between bubbles of different sizes. More generally, experiments with natural and synthetic three-phase magma have shown us that textural heterogeneities develop under deformation, including the formation of shear bands and ruptured bubbles. And these must have an important influence on rheology. They also become more important at higher concentrations, and as for the two-phase cases, work so far has focused on dilute and intermediate suspended fractions for three-phase materials. Heterogeneities are also likely to influence the failure of magma, and whilst the failure of pure melt is fairly well understood, most natural magmas are complex three-phase mixtures at the point of failure, and much more work is required to understand the conditions under which three-phase magmas fail. This is crucial to our understanding of the fragmentation process and whether magma erupts explosively or effusively. Some of the frontier topics I have identified simply require more work of the sort that has gone on for years, but there are also new tools available to us which are likely to have a transformative impact. For example, in situ X-ray tomography is already having a major impact across the geosciences, and in rheology, synchrotron source tomography allows us to image multi-phase samples in 3D during deformation. As shown in this example here, you can see a spindle rotating within a cup, and you can see a bubbly magma being sheared. This technique will be invaluable as we attempt to build models for multi-phase rheology that account for the interactions amongst the suspended particles and bubbles. As I mentioned earlier, disequilibrium in natural systems, which leads to crystal and bubble growth, has an important effect on rheology, which is hard or impossible to replicate with analogues. And there's a new generation of high-pressure, high-temperature rheometer that's under development, which will allow rheometry to be conducted on samples of natural magma that are undergoing natural pressure-temperature pathways that are relevant to the subvolcanic plumbing system. There are also new numerical tools at our disposal, and simulations of deforming multiphase materials are moving from 2 dimensions to 3 dimensions. When combined with experimental rheometry data, particularly rheometry data from XRCT analysis, this will be hugely valuable in developing new rheological models that account for phase interactions at the microscale. Ultimately, our desire to understand magma rheology is motivated mainly by a deeper desire to understand how magma and lava flow. Multidisciplinary approaches that integrate field, UAV and satellite observations, textual analysis, laboratory rheometry and numerical modelling are helping us to close the gap between the theory of rheology and its practical application. I'll move now to a brief case study that demonstrates how our current understanding of multiphase rheology can help us to understand the behaviour of lava flows. I was fortunate enough to be on sabbatical at the Hawaiian Volcano Observatory in the first quarter of 2015. At this time, the Pu'uo'o eruption on the East Rift Zone of Kilauea had, for the bulk of the previous 30 years, been feeding a well-established lava tube system that had transported lava around 11 kilometres to the ocean. And in recent years, it had posed little threat to dwellings and infrastructure. But in late 2014, new breakouts started feeding flows towards the northeast and eventually threatening the town of Pahoa that was a little over 20 kilometres away. During autumn of 2014 and spring of 2015, flows repeatedly advanced to within just a few hundred metres of the town, but each time they stopped short and each time the distal part of the nascent lava tube system broke down. Here we are looking back towards Pu'u'ol from above the town of Pahoa. Here's Pu'u'ol in the distance, and you can see how close the flow front reached to the town on successive occasions. And of course the question is why? Previously, robust lava tube systems had repeatedly developed that were able to transport the lava the 11 kilometers from Pu'u'ol to the ocean, but seemingly they were unable to develop over the 22 kilometers to Pahoa. In order to try and understand this better, I undertook a sampling campaign in collaboration with colleagues from HVO and the University of Hawaii to see whether we could learn anything from the multi-phase characteristics of the lava. We sampled directly from breakouts at 3 different locations, each time taking lava from within a few tens of meters of a breakout point from the nascent lava tube system. The samples were immediately quenched in water to preserve the textures, and the sites were about 1 kilometer, about 4 kilometers, and about 22 kilometers down tube from Pu'u'ol. In this video, you can see the lava at site 1. You can see that it's loose and mobile, and it's progressing as a series of broad lava tongues. At site 2, nearly 4 kilometers down the nascent tube system, you can see that the lava appears more sluggish. The breakout flow that's being produced has a more mounded morphology, and the lava is flowing more slowly. At the most distal site, that's around 21 kilometers down the tube system, you can see that the lava is very notably more viscous. And as a consequence, the breakout flows are forming a much more rugged topography on the flow field. So we made thin sections of each of the samples that were retrieved from the 3 sites, and we observed them using SEM. We noted that in all cases the crystals were much smaller than the bubbles, which means that we can treat the 3-phase material as a suspension of bubbles in an effective medium comprising the liquid plus crystals. And we used this imagery to determine the crystal fraction in the glass, and found that it increased only modestly from around 8% at site 1, so 1 kilometer down the tube system, to around 22% at site 3, near the distal end of the tube system. We also determined the bubble volume fraction using Archimedes' principle by weighing the samples in water, and found that it decreased substantially from around 70% at site 1 to around 20% at the most distal site. Putting this together, we reconstructed the expected viscosity of the lava at each of the 3 sites. Here we plot viscosity against distance down tube from the melt. Here in the middle you can see the computed viscosity of the melt phase, which takes into account the cooling of the lava as it's progressing down the tube system, and also any changes in composition as a result of crystallization. And here you can see the multi-phase rheology. At each of these sites, you note that the viscosity spans a range which depends on the capillary number, and in all cases the low capillary number is associated with the highest viscosities, and the high capillary number regime is associated with the lowest viscosities. So putting this together, we can see that there are 2 important changes that take place as the lava flows the 22 kilometers down the tube system. Firstly, in general, the viscosity is increasing modestly down tube, and this is mainly as a result of crystal growth, but also as a result of the slight cooling that's leading to an increase in the viscosity of the suspending silicate melt. More interestingly, we can see that the range of viscosity that the lava might exhibit with changing capillary number decreases dramatically as the bubble fraction decreases down tube. And this second point is important because it offers an explanation for the tendency of the lava flows to stop short of the town of Pahoa. At the most proximal site, the viscosity could vary by a factor of around 25 depending on capillary number, from about 15 Pascal seconds in the high capillary number regime to around 420 Pascal seconds at low capillary number. This manifests as a strong shear thinning tendency which promotes localization, flow tends to focus on the fastest flowing breakouts where the viscosity is lowest. This in turn promotes the formation of lava tubes, which provide effective transport pathways insulating the lava. By contrast, at the most distal site, the viscosity could only vary by a factor of about 2 with capillary number, from around 280 Pascal seconds in the high capillary number regime to around 550 Pascal seconds in the low capillary number regime. This much more modest shear thinning behavior means that localization is less favorable and breakouts of different sizes are likely to coexist, promoting the formation of a more diffuse flow field that does not develop a robust lava tube system and is more prone to cooling, which ultimately halts the flow. So a tentative and perhaps unexpected conclusion here is that the evolution of the flow field was likely influenced more by the loss of gas bubbles than it was by the growth of crystals as the lava was transported from Pu'uo'o downflow. I'd like to finish with a brief personal perspective on the most pressing challenges for the discipline. Firstly, I think further experiments are required to populate the ternary phase space with rheological data. We have fairly good understanding of pure melts and of two-phase suspensions of bubbles in melt and of particles in melt, but we have a very poor understanding at the moment of the central region of this ternary phase space. Related to this, we need a theory for phase interactions. Once we get to intermediate and concentrated suspensions, interactions dominate, and direct observation of interactions through X-ray computed tomography and direct numerical simulations offer a new way forward here. We also need to develop ways to account for sample history. Magma experiences dramatic changes on its journey through and over the crust, and the history of these changes up to any point in time influences its rheological response at that point in time. Related to this, we need to develop ways to deal with disequilibrium. Magma is out of equilibrium for much of its journey through and over the crust, and this leads to chemical, structural, and textural disequilibrium that all influence rheology. Experiments on natural materials under disequilibrium conditions are essential for progress here. Finally, we must remember that the purpose of investigating magma rheology is ultimately to help us develop better models of magma and lava flow. Rheological models should be couched in terms that support implementation in numerical models of fluid dynamics, and these models need to account for variations in rheology over space and time. I'd like to finish by thanking my colleagues in Durham who provide a wonderfully stimulating and supportive community. I'd also like to thank the students and postdocs who have chosen to work with me over the years, and you can hear from 6 of them, shown here in italics, during the rest of this meeting. And finally, I'd like to express my great debt of thanks to the many volcanologists who have acted as mentor to me over the years, and I dedicate my award to them. Thank you.